We are about to launch into counting and cardinality. And as we do that, we want to think about making our instruction explicit so that students really understand this counting and cardinality. And as we talk about making our instruction explicit, we're always going to think about this clear model where we construct a plan, lead by modeling, engage in practice, apply independently, and then refine with data. And we do all of that there so that students can do the math. That is, engage in that transfer and inquiry. As we get into counting, one of the things that students will work on very early on is understanding quantity. This means that they're going to explore different notions that sets and things have a value, but we might not formalize the counting process just yet. Some of this may occur through subitizing. Subitizing is being able to instantly know how many. For example, I can subitize these dots and say there's 6, or here there are 3. On this playing card, I see 7 spades. Maybe I can even subitize these fingers. I see 1 and 5, or maybe I can subitize these counters in this 10 frame and I can see that there's 4. Now, could I count these 1, 2, 3, 4? Sure. But also, could I subitize and just say, I see 4 counters? Yes, I could do that as well. But not all students might be great with subitizing, and that's okay. And so that's when we are going to bring in our practice with counting. There are 5 counting principles. You can see them listed here, and we're going to talk about them in detail. And these counting principles are absolutely important for young children as they learn to become efficient counters. So we're going to break down each of these principles in detail. So first, let's talk with stable order. Stable order is knowing the number names in order. So you know them and I know them, but let's say them together. The number names in order, starting with 1, include 1, 2, 3, 4, 5, 6, 7, and so on. These number names are absolutely essential to know. We end up memorizing them. There are parts of mathematics where it's okay to memorize. And if we don't have this stable order, everything else that we do in counting is going to be almost impossible to do. So we are going to do a lot of activities to help students with their stable order, a lot of repeating activities, a lot of echoing activities, and just a whole lot of practice. First, students might practice their stable order counting 1, 2, 3. Maybe then we go 1, 2, 3, 4, 5. And I'm pointing to these visuals, but I also don't have to have a visual. I can just say these number names in order. And then eventually students will have stable order to 10, to 15, to 20, and to so on. There is a correct counting sequence, and I think this is always super interesting as I think about the emphasis on the alphabet song. You all know it, A, B, C, D, E, F, G, right? We all know that. We all learned it very, very early on. But not all of us have a counting song. And now I want you to think about those two things. Which of those is actually more important? Is it important early on that students know their letter names in order, alphabetic order? No, it's not. It's just helpful that they know all the letter names. But you know what is really important is that students know the number names in order. And so that is the principle of stable order. Our next counting principle is the idea of one-to-one correspondence. So I have to take my stable order knowledge and then I'm going to apply it as I count objects. Maybe I'm counting manipulatives. We'll do an example of that in just a few minutes. Maybe I'm counting these pictorial bears that I see presented on this slide. But as I count, each object is going to get one count and only one count, one-to-one correspondence. And if I don't have my stable order, it's going to be really, really difficult for me to count these bears. So maybe I count these bears as 1, 2, 3, 4. That was kind of fast there. Let me go back and do that again. 1, 2, 3, 4. Notice how I used my stable order and gave each bear one count and only one count. So that is the counting principle of one-to-one correspondence. And really, you don't ever do that without stable order. So we have to have both of those counting principles in order to be able to count these bears. But that brings us to the third counting principle, which is the counting principle of cardinality. Cardinality is understanding that if I count these bears, The last number name that I say, or maybe you think about that as the last count, that tells us how many are in the set. Now, cardinality typically comes after students have some initial skill with stable order and one-to-one correspondence. And you might see this. Sometimes we see students count these bears, 1, 2, 3, 4. And then I ask, how many bears? And they might say 7 or 2. They know that there's a numerical response required, but they may not actually connect their counting to how many are in the set. And so here's where we just have to ask a lot of questions about, well, how many bears are there? So let's do that again, and I'll ask that question. So let's count. 1, 2, 3, 4. How many bears? 4. There are 4 bears in this set. So there we took our stable order, the number names in order. We applied that to one-to-one correspondence. Each bear got 1 count and only 1 count. And then we paired those with cardinality. That is how many bears are in the set. That's the last number name that we said. Now, those are the 3 essential counting principles: stable order, one-to-one correspondence, and cardinality. But there are 2 other counting principles. Oh my gosh, look, I forgot that my little bears will count like that. And then there are 4 bears in the set. Now, there are 2 other counting principles that are nice for students to understand, but I might suggest that they're not essential. So if students don't have these 2 next counting principles, I'd practice it a little bit, but I wouldn't stress out that much about it. But I would stress a lot if students don't understand stable order, one-to-one, and cardinality. The 4th counting principle here is order irrelevance. So it does not matter what order I count these bears in. The order is irrelevant. The number of bears in this set will always remain the same. So I could count these bears 1, 2, 3, 4. I could also count them, let's see, 1, 2, 3, 4. Or I could also count them 1, 2, 3, 4. The order of which I counted these bears, whether I counted them this way or that way, maybe I counted them from the inside out or from the outside in, it doesn't matter. The order can be irrelevant, but the cardinality of this bear set will always remain the same. And then this 5th principle of abstraction is another principle that's nice for students to understand. But again, I really focus a lot on those first 3 counting principles. But this is the principle of abstraction. So far I was counting those bears and they were all the same, and it's just like this nice clean set, wasn't it? But let's say I get a little crazy today and I pull out all of these objects here and I say, this right here is a set of objects. And if I say that this is a set of objects, well, my goodness, I can count this as a single set. The set can be abstract, but if it's a set, I can count it as a single set. So let's count these objects here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. How many are in the set? 13. There are 13 objects in this set. So that is the counting principle of abstraction. The set can be, it doesn't have to be all nice bears, it doesn't have to be all green things, it doesn't have to be all orange sticks. It can be any set of items, and if I ask to count that set of items, I can count those, and that can be an abstract set. So those are the 5 counting principles. Now, all of the examples I just showed, those had representations or pictorial images, but I want to do a little bit of this with manipulatives because that's how we are often practicing counting with young students. So let me go ahead and get some of my favorite manipulatives out, and I'll see you in just a moment. All right, so here are some manipulatives that I might use to help students practice their counting. First, let's count this set of square counters. So if I want to count these, I'm going to think about my stable order, 1, 2, 3, 4, 5, 6, 7, 8, and so on. Then I'm going to think about using my one-to-one correspondence, so each item gets 1 count and only 1 count. And then at the end, I'm going to ask how many are in the set to show how many are in the set. That's cardinality. So let's count these counters. 1, 2, 3, 4, 5, 6. How many are in the set? There are 6 counters in this set. I have 6 square counters. Now I already lined up my manipulatives here, and I lined up my motors, which I'm going to count next, but I want to go ahead and be a little bit messier with my counting and talk about some strategies that are helpful for students as they are organize their counting, especially if I have a messy set of motors just like I have there. Now, one of the things that's helpful as we help students with their counting is teaching students to do what I like to call partitioning and tagging. So if I have a messy set of counters like these here, I'm going to partition a counter. I'm going to partition it by taking it from the set, and then I'm going to tag it with a number name. So for example, I take this car and say 1. Then I take another motor and tag it with 2. I keep going, tag 3. No, keep going, tag 4. Keep going, tag 5. Keep going, tag 6. Keep going, tag 7. Keep going, tag 8. And keep going, tag 9. So I had all these counters, and when I partitioned and tagged them, I now see that I have 9 counters in the set. And could I count those again? 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 counters in the set. When you do something like partitioning and tagging, it gives students some organization to their counting. Because if I just had all these counters in this messy set like this, I could see that some students might count these counters right here like this. 1, 2, 3, 4, 5, 6, 7, 8, right? Did you realize I accidentally missed one? Or maybe students might count this set like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What did I do there? Oh, I counted 1 twice. When it's messy, my counting might not be clean. But if I do things like line them up or partition and tag them, it's a lot easier to count. So again, 1, 2, 3, 4, 5, 6, 7, 8, and 9. There are 9 counters in this set. Now you can use any manipulative. Fingers are a really good counter here. You can also use drawings. There are hundreds of representations that we can use to help students practice their counting. All right, so that was a whole lot of information about counting, and that brings us to activity 1. In this activity, you are going to fill in this table with the definition of each of these counting principles, and then I'd like you to come up with at least one example of how you would practice this with students, or what this is going to look like when you teach this to your students. Have fun with this activity, and I'll see you on the flip side.